Okay, this is section 2.2. We're going to talk more about limits today, and limits from the left, limits from the right, when limits exist, when they don't, that kind of thing. We talked about the concept of limits last time. So the limit of a function says to find the tangent to a curve or the velocity of an object, we now turn our attention to limits in general and numerical and graphical methods for computing them. So we're talking about the behavior of this function f of x equals x squared minus x plus 2 for values of x near 2. So near means somewhat close on the right, somewhat close on the left. What's it going to look like? So we did this before where we plugged in values in our functions. As we got closer and closer to 2, you can tell here, as we get closer and closer to 2, what number it's approaching. And this is from the left-hand side. We start at 1 and get to 2. Now from the right-hand side, we start at 3 and go down to 2. And you can tell by this number and this number, they are getting close to the number 4. Okay, so that would be our limit. From the table in the graph of f, a parabola shown in figure 1, we see that the closer x is to 2 on either side, the closer f of x is to 4. Again, same thing we noticed. Okay, the value of the function is going up to 4 from the left. The value of the function is coming down to 4 from the right. Now, this is what it would look like if we write it using the limit terminology. So it says to express this by saying the limit of the function f of x equals x squared minus x plus 2 as x approaches 2 is equal to 4. This is how we write it. Again, the limit as x approaches 2 of x squared minus x plus 2 equals 4. And then we have the intuitive definition of a limit. So again, it's in English, it's the limit of f of x as x approaches a equals L. Now, I'm bad about reversing those, and I don't really think it matters. I usually say the limit as x approaches a of f of x equals L. I don't really think it matters. Now, alternative notation is this. I don't know that you'll see that very often. It's pretty standard to use this limit notation. That's all they are getting at. But one thing I want to point out, it is as x approaches a, not as x equals a. So you can have the limit of a function at a particular point without actually having it equal that number at that point. So I'll explain that here in a minute. Figure 2 shows the graph of 3 functions. Note that part C, f of a is not defined, and in part B, f of a does not equal L. So this is what I was talking about. This continuous function, this blue line here, again, as x approaches a, whether it's from the right or the left, okay, we see if we travel up here, we see that the limit is L. Well, that's all great, good, and fine. On this one, as x approaches a from the right and the left, again, we see that the value of the function approaches this point. But you'll notice this is an open circle. So the limit of this function, okay, the limit would still be L, even though f of a does not equal L. F of a is actually down here, whatever that value is. I don't know what that value is, but that's the value of the function at that point. So the limit does not have to be the same as the actual value of the function at that point. Okay, that's what they're getting at. And then this one again, as x approaches a from both sides, again, we're getting close. And this is just simply undefined at that point. Okay, the value of the function at point A does not exist, but the limit does. Okay, so this would be f of a does not exist. On your homework, they'll ask you to put in a D in E if there's no answer. Okay, so the value of the function at point A does not exist, but the limit does. So guess the value of limit x minus 1 over x squared minus 1 as x approaches 1. Okay, notice that the function is not defined when x equals 1, but that doesn't matter because the definition of the limit says we consider values of x that are close to but not equal to a. So in this case, we know by the denominator, right? If we factor that, what values can x not be? It can't be a positive 1, and it can't be a negative 1. But yet we can still find the limit, because the limit is the value of the function as it approaches that number, not what it equals at that number. Okay, so again, that's the differentiation they're trying to make. So again, you can tell here as x goes from the left up to 1, it approaches a half, and from 1.5 down to 1, again, it approaches a half. Okay, but if you tried to put a 1 in, figuratively speaking, it's not defined because we can't divide by 0. Okay, so this is, if you guys remember way back in Algebra 2, these are the ones where we were talking about polynomial or rational expressions, and we talked about vertical asymptotes and horizontal asymptotes and holes. This would be the hole where something isn't defined. Anyway, notice here, that's a big open spot. Okay, but again, the limit still exists. So one-sided limits. Now we are talking about, I don't know if you can see down here, this is a minus. We are approaching 0 from the left. And here the plus, we are approaching 0 from the right. So you will see sometimes we can have different limits approaching the same number depending on what direction we're coming from, particularly if it's a piecewise function. Do y'all know what I'm talking about when I say piecewise function? Yeah, where there's 2 or 3 different parts and it gives different domains for each of those parts. Okay, on a piecewise function, you can have different limits if you're coming from different directions on one of the endpoints of those domains. So this is our left and right limit. So it says the notation t approaches 0 minus indicates we consider only values of t that are less than 0, and t approaches 0 positive indicates that we consider only values of t that are greater than 0. Again, in my mind, I'm a picture person. I like to think of it as approaching from the left, approaching from the right. So definition of one-sided limits. So here again, they've got a notation here. It says the left-hand limit of f of x as x approaches a, or the limit of f of x as x approaches a from the left. Quite honestly, that's usually the phrase I use, from the left, because again, in me, it's a visual person. So I usually think of it kind of in my mind's eye. So as I'm visualizing the picture of the graph, I'm thinking as it gets there from the left. Notice definition 2 differs from definition 1 that we had earlier, only in that we require x to be less than a. So the only thing that differed was the little minus on the a. Okay, and it's always kind of up in the exponent spot if you were to type it out yourself. So now we're talking about right-hand limits, or from the right, okay, as we're approaching. This is the left-hand limit, as I circled this minus. This is the right-hand limit, as I circle that plus, okay? This, again, will make more sense as we actually look at some problems, but here's the kicker. This is a big one, and you kind of look at it and think, well, duh, but the limit of f of x as x approaches a equals L if and only if. First of all, what does if and only if mean? If and only if, again, I'm a visual person. I like to visualize it as going both ways. It's a double arrow, okay? If you're actually writing this, math geeks are good at finding shortcuts, and it's, if you ever like read a math paper, I don't know why you would choose to do that on your own time, but they'll shorthand that and go IFF, if and only if. But it's a double arrow. It goes both ways. So limit of f of x as x approaches a equals L if and only if the limit of f of x as x approaches a from the left and, or equals L, and the limit of f of x as x approaches a from the right equals L. So if, let me back up here. We can only find the limit at a particular point if both sides approach the same point. Okay, so if both sides approach it to the same place, If our left-hand limit equals our right-hand limit, then we can say we have a hard generalized limit. Okay, but if I've got, let me just, if I've got some function, and I'm going to say this is 3, okay, and I'm going to say this is 5 and this is 2, okay, and these are my functions. Maybe I should put colors on these. Again, I'm just pulling this out of my hiney, so hang with me here. If I say that the limit as x approaches 3 from the left of f of x, what would that be? What's the limit of f of x as x approaches 3 from the left? 5. Okay, that's what it's getting close to, right? Down here, the limit of f of x as x approaches 3 from the right is what? It's 2. So this side I'm approaching 2. This side I'm approaching 5. Okay. So does the hard limit as x approaches, as x approaches 3, what's the hard limit of f of x? This is D and E. That's what I was alluding to. Your left and right hand limits have to be the same at a particular point for there to be a hard limit without a direction arrow. Does that make sense? Okay, they have to be the same. Coming from either direction, they'd have to equal the same number for there to be a hard limit without a direction. Does that make sense? Okay. Well, come on, baby. There we go. So the graph of function g is shown. Use it to state the values if they exist of the following. So much better than my sad graph on the previous one that I drew. Limit of g of x as x approaches 2 from the left. As x approaches 2 from the left. Limit would be 3. Again, from the left would be up here. That would definitely be 3. Are we okay with that? Now, the limit of g of x as x approaches 2 from the right. So from the right, if I'm going this way, what's it approach? 1. So what's the limit of g of x as x approaches 2? Does not exist. Because those are not the same. Does not exist. So part D here, limit of g of x as x approaches 5 from the left. So from the left, what is that? 2. Are we okay with that? From the right, that would be from this way, approaches 5. Also 2. So what's the limit of g of x as x approaches 5? 2. Okay, now, does that mean the value of the function at 5 equals 2? No. G of 5 equals what? G of 5, yeah, we're going to call it 1, okay? And that's okay. The limit as it approaches 5 can be different than the value of the function at that point. So all of that is correct. Does that make sense? Everybody see those? Difference in limits. Okay. And I think here they're just walking us through what we just did. Yep, I already did that. Infinite limits. This would be like an infinite limit. Again, I'm a visual person, so I'm always thinking graph. That would be like when you had a vertical asymptote and your graph gets really close to it. Okay, so like you have some graph, this does not match what's necessarily on the screen, but you have some graph and say this is 2. Say you have a vertical asymptote. Okay, you have some rational function, whatever our f of x is. It's something over like x minus 2. So we have a vertical asymptote at positive 2. So whatever, if this is my function and it approaches this or it approaches this, this would be infinity or negative infinity limits. Okay, it would be positive infinity limit if I'm approaching 2 from the left, and a negative infinity limit if I'm approaching 2 from the right. That's all they're getting at here. Okay, so, and it says means the values of f of x can be arbitrarily large by taking x sufficiently close to a but not equal to a. So, different ways you can say it. This is a good example. I guess they kind of assume that these would have arrows. And again, this would be a vertical asymptote, okay, at x equals a. Vertical asymptote here. So my limit of f of x as x approaches a equals infinity. Why? Because it approaches infinity both from the left and from the right. Okay. Now the one I had on the previous slide, that would be it does not exist because it approached it to infinity from the left and negative infinity from the right. Same thing here, approaching negative infinity. Again, I'm assuming that they have arrows here. I think we're good. So again, illustrations of the 4 cases. I think now that we understand how the right and left limits work, you guys can kind of understand these. One thing that I want to point out is all of these PowerPoints I have posted in Google Classroom, okay? And this sad little recording that I'm making now for Troy and Austin will also be posted. So if you guys ever want to go back and listen or go through the PowerPoint again, they're there for you, okay? So more definitions of limits, whether it's positive infinity, negative infinity. So again, find the vertical asymptotes of f of x equals tan x. Do y'all remember what the vertical asymptotes are? First of all, tangent. What does tangent equal? What's its identity? Okay, no, that's how you, I'm talking identity, like what's it made up of? Sine over cosine. So tangent x, if you remember, is sine x over cosine x. So where is cosine x? 0. That would be its vertical asymptote, right? Do you remember? When cosine x equals 0. No? Okay, we're thinking pi's or pi over 2's, or so when is it? Do I remember? It's actually pi over 2. Pi over 2 to negative pi over 2. This is what your tangent function looks like. And they're probably going to add a nice pretty slide after this. But so your tangent function looks like this when it's graphed. Okay? And it has a vertical asymptote every pi. Like its period is pi. Okay? And its base period is negative pi over 2 to positive pi over 2. It's positive in the first quadrant and negative in the fourth, essentially. Okay. So, and it keeps repeating. So like if this is pi, then this over here would be 3 pi over 2. This would be another, and it would keep repeating. So could you say that the limit of tan x as x approaches pi over 2, does it exist? I heard a no and I heard a yes. So the limit as x approaches pi over 2 of tan x, does that exist? Does that exist? That's what I'm asking. Think about what we talked about earlier. In order for a limit to exist, it has to be the same approaching from the left and the right. So as x approaches pi over 2 from the left, what does it approach? Positive infinity. From the right, what does it approach? Negative infinity. So does the limit of tan x as x approaches pi over 2 exist? No, does not exist. Because again, one direction it approaches positive infinity, the other direction it approaches negative infinity. Okay. I'm going to quit there. Okay. So this should help you with your homework. Let me see. I was going to pull up. Why won't it let me? That's not what I wanted. Oh, that's right. Part of my thing is cut off. Okay. That doesn't help me.